Hello everyone, and welcome to the best machine learning tutorial that I've ever filmed, where we will dive deep into Scikit-Learn, which is a popular open source library that is so user-friendly, it will blow your mind. It is the perfect place to start your machine learning journey. And our goal here is to learn it by example, following a step-by-step professional workflow, where we'll talk about training, testing, evaluation, optimization, polynomial features, and even hyperparameterization. So that by the end of this video, you will fully understand all of it and none of these words will sound scary anymore. So are you ready? Let's roll. So let's start by installing Scikit-Learn with our WSL terminal. We will create a new working environment with conda create-n. We will call this environment ml_env, and we will install Python 3.12 init. Then we will activate this environment with conda activate ml_env, and we will then pip install Scikit-Learn inside it. Additionally, we will install an IDE named Jupyter with pip install Jupyter, with no typos, of course, okay? Not ibstall, install. And beautiful. Now that everything is installed, let's actually encapsulate our project inside a folder. So let's create a new directory with mecdir, and we will call it ml project. Then we will navigate to this directory with cd ml project, and we can then go ahead and launch our Jupyter instance with Jupyter Lab. Now, the first thing we need in a machine learning project is data. We need to learn a dataset really well in a process called training, and then based on everything we've learned, we will make an informed guess. Now, this guess is what we call a prediction. So for example, from sklearn, we will import datasets. And then we will load our dataset directly from Scikit-Learn with datasets.fetch_California_housing, followed by an empty set of round brackets. Then we will assign this expression with no typos to a variable housing. Now, if you're curious to see what this dataset stores, let's go ahead and print our column names with print housing.feature_names, and we see that we're dealing with things like house age, average rooms, location, and so on and so on. Now, once we know how our features look like, let's go ahead and extract them with housing.data, and we will assign them to a variable x. Now, you may have noticed that the most important piece of information about our houses is not really stored as a feature. It is stored separately as housing.target. And I'm of course talking about the dollar value of these houses, which is probably what everyone is curious about. And when it comes to targets, we are always assigning them to y. And we are always fixing our typos once again. Okay, now if you're curious to see how these two look on the inside, let's go ahead and print our very first sample and our very first target. We will do so with print x in the index of 0, as well as print y in the index of 0. Let's go ahead and decipher the results together, where we see a group of people whose yearly income is about 83 grand. They live in houses that are about 41 years old. They have roughly 7 rooms in their house. So living rooms, dining rooms, bathrooms, and so on. And even though they have so many rooms, they only have a single bedroom. Now, this group has precisely 322 people who are working in the same occupation and living in the same area. Now, when we look at the target right below, we can see that the average value of their houses is about $452,000. And great. So now that we know exactly what kind of data we're dealing with, let's go ahead and split it into test samples and training samples. Now we will do this automatically with a special scikit-learn function from sklearn.model_selection. We will import train_test_split. Then we'll go ahead and copy this function and we will call it right below our x and y variables. We will then pass our features x and our targets y into it, along with a test underscore size of 0.2, also known as 20%. So we are basically reserving a fifth of our data for testing and evaluation, while the rest of the data will be used for training. Now, this expression unpacks into 4 different variables, and let's split it into several lines, because as you may guess, my head is about to block all of them. Okay, so let's go ahead and unpack it first into x_train, then x_test, followed by y_train, and then y_test. Whew, and beautiful. We have now officially split our data into test samples and training samples. Now, another thing we can do here is we can set something called a random_state. Now, in my case, I will set it to 432, but you can set it to any kind of integer you'd like. And the idea behind this random state is instead of just randomly shuffling our data and pushing some samples into the test set, pushing some samples into the train set, we are shuffling these samples in a very specific order. And then, if we do so, we can recreate the exact same workflow, not just on our end, but also on somebody else's end. So let's see a quick example, okay? So if we have our random state, and then we try to print our first sample of X train, as well as our first target of Y train, no matter how many times we will rerun this cell, we will always get the exact same numbers, okay? There you go. However, if we comment out this random state and we run this cell once again, we are now dealing with different numbers. And every time we will rerun it, our numbers will change and the shuffling will be absolutely random. So it is very common to have this random state on, and this will ensure that our shuffling is consistent. Great, but how exactly do we train with scikit-learn? Now, training with scikit-learn is actually easier than you think. We first choose some kind of an algorithm, in my case, linear regression, which I covered in great detail in a recent tutorial. And we will import it from sklearn.linear_model. We will import the linear regression class. Then we will copy the class name and we will initialize it at the very bottom, right below our train and test split. We'll of course paste it, and don't forget to add an empty set of round brackets to the very end. Then we will assign it to a variable model. Now, to train this model, all we need to do is type model.fit, passing it our X train and our Y train data. And boom, that was training. Now, our model will go sample by sample and compare each set of features to its target. And then at the end of the process, our model will be an expert to our entire training data. But that's not all. We will also need to make sure that our model learned the data rather than just memorizing it. And for this, we will need to evaluate it on data it has never seen before. And that's exactly why we reserved our X-test data right above. So right below our training function, we will go ahead and call model.predict, and we'll pass it our X_test data. Then we will assign, we will fix my typo, okay, model, and we will assign this expression to y_pred, as in y prediction, the prediction of the target. And in fact, it is crucial that our predict function will know nothing of the y-test target that we got from the dataset. Why? Because that's the exact value that our model is trying to guess. So given these features that we see in X-test, what kind of target do you estimate that it has? And then we store this target as our y-pred. And then lastly, to determine just how successful and intelligent our model is, we will compare our ypred to our ytest targets. Okay? For this, we will need some kind of evaluation metric. In my case, from sklearn.metrics, I will import the R2 score. We will then copy this function name, and then right below fetching our prediction, we will go ahead and call R2 score, and we will pass it our ytest and our y_pred data. Okay, so we are comparing the actual values of our test set with the predicted values that our model gave us. Okay, and then we store this score as R2. And actually, let's print it right below, getting rid of the rest of our print statements, just R2. Okay, and let's see the verdict. And in our case, we get a score of 0.6. But it doesn't mean that our model made the correct prediction in 60% of the cases. This is what the accuracy score traces. In our case, with R2, it means that our model understands 60% of why the house prices go up and down. The other 40% is a mystery. And even though a score of 60% is not too bad, this is just the beginning. This is what we call a baseline. And in fact, the whole idea of machine learning is taking this baseline and keep improving it further and further with slight modifications to our code. And that's exactly what we'll do in the rest of the video. We'll take this model from 60% all the way to 70% and 80% and so on. We will do this gradually together. Now, to make our model smarter, we do something called optimization. And one way to achieve it is by introducing polynomial features, where we take our existing 8 features and we then expand them, generating way more data than before. And in most cases, it produces better results. So for example, from sklearn.pre-processing, we will import the Polynomial Features class. If I only remember how to spell it right, okay? Polynomial features, hopefully. We will then copy this class name and let's initialize it right above our test and train split. Let's paste it and let's add an empty set of round brackets to the very end of it. Then we will assign this class to poly. And now once we have a polynomial object, we can then go ahead and call poly.fit_transform, passing it our x value into it, which of course represents our features that will be expanded as a result. So let's quickly reassign it back to x. And also let's have a look at what happens in the background. Okay, let's print x.shape right above and right below our transformation. Now let's give it a run. And okay, so not only have we increased the number of features from 8 to 45 of them, but we have also increased our R2 score from 0.6 to 0.66. So basically, our new model is now 6 points smarter than our baseline. Now, if you're curious about what on earth those 45 features store, well, in addition to the existing 8 features, we are also storing their squares. So for example, when we have our number of rooms column, right beside it, there will be another column called number of rooms squared. So if the number of rooms stores 7, the number of rooms squared will store 49. And we repeat it for each feature. Now, in addition to those squares, we also multiply each feature by the other. So we multiply the number of rooms by the population. We multiply the median income by the occupation or the latitude and so on, generating 36 extra columns. And now because we have extracted so much more information from our existing data, our model makes much better guesses than before. Okay, but how do we know if this linear regression algorithm that we have randomly chosen earlier is the best match for our kind of data? What if switching this algorithm to something else is a much more effective way to optimize? Let's verify that. For this, we will import 2 new algorithms from sklearn.ensemble. We will import the gradient boosting regressor and the random forest regressor classes. And actually, let's split it into several lines because I think my head is about to block some of it, okay? There you go. And now let's go ahead and copy these two class names. Ooh, I found a typo. Regressor, okay? And now let's copy these class names and let's paste them right under our linear regression model. Then we will add some round brackets to the end of these class names and we'll assign the gradient boosting regressor to GBR and then random forest regressor to RFR, which makes our linear regression model LR. Then we will iterate over all these lovely algorithms with for I in a list with LR, GBR, and RFR. We will then indent all these lines of code below this for loop, just so they're part of the for loop. And then everywhere we see the word model, we will replace it with I. And we'll do this for the fit method and for the predict method. Then at the very end, when we print our R2 score, we will also print the name of the model given by I. Beautiful. Now let's give it a quick run just to see the verdict. Now, once we are done training and evaluating all these models, we see that gradient boosting and random forest work much better for our kind of data. We are now 20 points above the baseline in both cases, which is very impressive. And the idea is we never know what kind of algorithm will work best until we actually try them. And that just shows you how important experimentation is when it comes to machine learning. Now, one thing you may have noticed is that random forest took a very long time to process. And in fact, our computer probably sounded like a spaceship about to explode or something. Now, if you'd like to fix it, all we need to do is we need to add an additional parameter, or in our case, the only parameter inside our random forest regressor object. This parameter is named n_jobs, and we'll set it to -1. Now, this special parameter tells our CPU to use all the available cores for the calculation. If we set it to 5, it will use 5 cores. If we set it to 10, it will use 10 cores. But -1 uses all of them. Now, if you'd like to speed up the gradient boosting as well, the best way to do so is actually by using an optimized version of this algorithm. It is called HIST gradient boosting regressor, and we will update it here as well as in our import statement. Now let's give it a quick run, and this time it will actually be quick. So not only did we just receive our results almost immediately, but we are also improving our gradient boosting by 3 additional points. So we are now 23 points above the baseline, which is wow. Tap yourself on the shoulder. This is good. So let's say we are happy with our scores. What do we do next? Well, another thing we can optimize is the parameters of our best performing model. So let's quickly copy our histogram gradient boosting model, and let's get rid of all these models altogether. And then at the very top of our for loop, we will paste this model and we will assign it to model. Then every instance of I within the for loop will be replaced with model. And now our goal here is to generate several instances of the same model, just with slightly different settings. In my case, I will play with a parameter named max_iter. And this parameter represents the total number of tree structures that our gradient boosting algorithm will generate before the training is complete. And the idea is the more trees, the more structures we have, the more complex the algorithm, and it might help us get better results. So let's quickly assign it to a value of I, our iteration variable, and then as iteration options, we will pass 100, which is the default number of trees. We will also pass 150 as well as 200, and I think it's enough for now. Okay, now let's give it a quick run. Okay, we see that the best score so far is given by 200 trees. So how about, let's say, 250 and 300 and 350. Let's see which of them is better. And okay, it looks like 200 is still the winner. Everything after that starts declining. But then the number of trees is not the only parameter we can experiment with. So how about if we add another parameter to the mix, one that is called learning rate? For this, we will create a nested for loop with for j in a list with the default 0.1 as well as 0.05 as well as 0.001. And then let's get rid of some of these numbers of trees. And actually, let's keep 200 because it was the best one. Okay, let's do 200, 250, and then 300. Now to make it work, we will need to indent the rest of our for loop, and we will also need to specify the learning underscore rate of j inside our gradient boosting regressor. And then at the very bottom, in addition to the I, we will also print the j and the R2. Let's give it another run, and let's see the verdict. And perfect! We see that nothing beats 300 trees with a 0.05 learning rate. And what we've done here is a process called hyperparameterization. Okay, a very long word, but a very important process. And while here we have only experimented with 2 parameters, in practice we will experiment with as many parameters as possible, optimizing our model further and further and further. So let's say we are perfectly happy with our 84% model and we don't want to optimize it further. Our last step is saving this model on our system so that we never have to train it again. For this, we will import a library named joblib, and then at the very bottom of our code, we will first get rid of these hyperparameterization loops. We will then fix our indentation, and then we will replace the iteration variables with the max iter of 350 and the learning rate of 0.05, which I believe was the best version of our model. And then we will also get rid of the iteration variables at the print statement. And then right after we are done training our model, we'll go ahead and save it on our system with joblib.dump. Now, the first value this method expects would be the model itself, and the second value is the name of the file that we would like to generate. In my case, my_model.joblib. And great, let's give this cell a quick run. And awesome. So now that we check our file system, we will find a brand new file named mymodel.joblib. Now, if we'd like to use this model in this notebook or in any other workflow, all we need to do is type joblib.load. We will pass the name of our file into it. And for the sake of experimentation, let's quickly assign it to a different model name. In my case, local model. And then we'll copy our predict and our toScore functions. We will paste them below, but instead of calling them on our model, we will call them on our local model. Now, if we run this cell, we get the exact same R2 score down to the smallest of decimal points, which means that these two models are perfect copies of one another. And thank you so much for watching. If you found this video helpful, please share it with the world. And don't forget to leave it a huge thumbs up and all kinds of comments. Now, if you'd like to see more videos of this kind, you can always subscribe to my channel and turn on the notification bell. I'll see you soon in an awesome tutorial. And in the meanwhile, bye-bye.